Assalamu alaikum. Welcome to the new class of physics after a long break. Today we will start a new chapter called physical optics. Optics, as you know, is a branch of physics that deals with light. And physical optics, when we discuss physical optics, we consider light as a wave. So in physical optics, we will consider light as a wave and we will see different phenomena of light which we can explain using the wave theory of light. So let me go further with a brief introduction, a historical introduction to this chapter. Have you heard the name Maxwell before?
Yes.
Yes.
Where have you heard the name Maxwell?
Electromagnetic.
Electromagnetic and electrostatic.
You have already studied about electromagnetic waves, and it was James Clerk Maxwell in 1860 introduced the electromagnetic wave theory, and he developed the idea that light is a kind of electromagnetic radiation. He did that because he found that the speed of light in vacuum, which is 3 into 10 raised to 8 meter per second, matches with the speed of electromagnetic waves. And light has almost all the properties of electromagnetic waves. So he developed the idea that light is a kind of electromagnetic wave or electromagnetic radiation. Later, Hertz. Have you heard the name Hertz before? What is Hertz?
Wavelength.
Not
Frequency.
wavelength.
No, the unit of frequency, right?
Yeah, Hertz is the unit of frequency.
Unit of frequency.
So, the unit of frequency is taken as Hertz as a honor to the scientist Henry Hertz, who produced and detected electromagnetic waves from electric source and confirmed Mach's prediction that light is an electromagnetic wave, and he did that in 1887. And due to this discovery that electromagnetic waves can be produced from an electric source, we are now able to enjoy a lot of things like radio, television, even our mobile phones. All distant communication is made possible because of this discovery. So we should owe to Maxwell and Hertz for their discovery on electromagnetic waves. Now, this happened in 1860s and 1880s, right? Even before that, around 200 years before, that is in 1678, Christian Huygens published the wave theory of light. See, this is Christian Huygens. You can see him with a wig, right? I wonder why in 1600s and 1500s, scientists used to put this wig. Even Isaac Newton, whenever I see his picture, there is a wig there. So
this is wig or real?
I think it is a wig. I'm not sure, but I think
I
it
guess
is a
they're
wig.
trying to
All
be
scientists
judgmental.
of that age, I have seen pictures like this. All of them will not be having hair of the same kind, right? I hope it's a wig. So Christian Huygens published the wave theory of light. That is in 1678. After 200 years, see the hairstyles changed. How only the people who lived in 1600s and 1500s will have so much of hair. I hope this is we. And the light phenomenon like reflection, refraction, interference, diffraction, etc., could be explained using this theory, that is wave theory of light. We have to admit that Christian Huygens is a brave, or he was a brave young man, because during that period, Isaac Newton was already a renowned scientist, and it prevailed Isaac Newton's theory of light, that light is made of tiny particles called corpuscles. So when that corpuscular theory was prevailing, this young scientist published this revolutionary work called wave theory of light. The scientific world was not ready to take it. And then another two young scientists, Thomas Young and Fresnel, experimentally showed that light exhibit all the phenomenon shown by light, other waves like interference, diffraction, etc. Only after their experimental discovery, Kristen Huygens' wave theory was accepted by the scientific world. So in this chapter, first we will see electromagnetic waves, electromagnetic radiation, some of their properties. Then we will see Kristen Huygens' wave theory of light, and we will also see some of the wave phenomena exhibited by light, like reflection, refraction, interference, diffraction, etc., and how all this phenomena can be explained using the wave theory of light. Is that clear? Is that clear to you? What we can expect from
Yes,
this
teacher.
chapter? Okay. So let us start by explaining electromagnetic waves. What is an electromagnetic wave? You already know that a wave is an energy which is transmitted, right? An electromagnetic wave is an energy transmitted as a result of electric and magnetic disturbances moving with the speed of light. And here, the electric and magnetic fields are perpendicular to each other and to the direction of propagation of wave. Here you can see a diagram. Here this orange line shows electric field. See, the electric field is varying in the y direction. That is, the electric field is going up and down. So it's varying in the y direction. And the blue line shows magnetic field. And the magnetic field is varying in the z direction. In which direction is the wave propagating? What is the traveling direction of the electromagnetic wave?
X.
X direction. So both electric field and magnetic field are perpendicular to each other and also to the direction of propagation of the wave. Just by looking here, can you tell me electromagnetic wave is a longitudinal wave or a transverse wave?
Transverse.
It is
Transfer.
transverse because you have learned in
Transverse, right?
Yeah, transverse, that's right. Because you have learned in mechanical waves that the particles vibrate perpendicular to the direction of propagation of wave in the case of transverse wave. So here the electric field and magnetic field are varying perpendicular to the direction of propagation of wave. So electromagnetic wave is a transverse wave and it is generated by acceleration of electric charges. So if a charged particle is moving in circular motion, it should generate electromagnetic waves because circular moving charged particles are accelerated charged particles. So that is how electromagnetic waves are produced by the oscillation or circular motion of electric charges or by making them pass at very high acceleration. Now, the direction of velocity of EM means electromagnetic wave, is the direction of the vector product E cross B. Here, E and B printed in bold represents vectors. We know when we write a vector, we write the letter and put an arrow above it. But if it is made bold in print, it means a vector. We know electric field is a vector, magnetic field is a vector. And when we take the cross product of two vectors, what will we get?
The scalar product.
Yeah, we will get a vector because it's called a vector product. So the velocity of the electromagnetic wave, which is also a vector, can be obtained by the cross product of E and B, E cross B. So we know that the vector product will be perpendicular to the two vectors which are multiplied. So the velocity is perpendicular to both the electric field and the magnetic field. Now, when light travels along x-axis in vacuum, the wave equation for electric and magnetic fields are represented like this. Here E is equal to E naught sine 2 pi by lambda Ct minus x. Here E naught and here B naught are called the peak values or amplitudes. You have already learned what is meant by amplitude. Can any one of you tell me what is amplitude or peak value? What is meant by the amplitude or peak value? The amplitude or peak value is the maximum value of that quantity. Here you can see the electric field varies in the y direction. It goes from 0 to a maximum value, come down to 0, then goes to a maximum value in the opposite direction. So here the electric field varies like a wave, or it varies like a sine function. And the maximum value of the electric field is called the amplitude or peak value of electric field, which is represented by E naught. Similarly, magnetic field is varying in this direction. So it's like a wave or a sine function that varies in the z direction. And the maximum value of the magnetic field or the peak value is represented by B naught. So E naught and B naught are the amplitudes or peak values of electric and magnetic fields. And lambda is the wavelength of the wave. So here sine 2 pi by lambda. And what is C? What is
Speed of
C? C is the speed of light. What is its value?
3 into 10 to the power 8 meter per second.
3 into 10 to the power 8 meter per second if it is moving in vacuum. Suppose the same electromagnetic wave is moving in another medium. So its velocity may be expressed by V. Then this equation will be like E naught sine 2 pi by lambda Vt minus x. There you have to consider the velocity of light in that particular medium. And t represents the time. So this equation represents the value of electric field at any time t as it is propagating. So what is x? X is the position of the wave because the position of the wave is changing along the x-axis. It is traveling along the x-axis. Now, if the wave was traveling along the y-axis, then here the variable will be y. Okay, so this is the wave equation that represents the electric field and magnetic field. Is it clear to you? You will have to memorize these equations. Can I proceed?
Yes, teacher.
Okay, so we have learned here what is an electromagnetic wave. You have to tell that it is energy transmitted as a result of electric and magnetic disturbances, and it travels with the speed of light, and electric and magnetic fields are perpendicular to each other and to the propagation of wave. And you also have to remember these equations, that is E is equal to E naught sine 2 pi by lambda Ct by x, and a similar equation for the magnetic field. Both change like a sine wave. Now, the speed of light is a special quantity. Do you know of anything which can travel at a speed larger than that of light?
Not yet.
Not yet. So
Not
we
yet.
haven't discovered anything which can travel at a speed which is larger than the speed of light through vacuum. So the speed of light through vacuum is related to some of the quantities, and here we are going to see some equations which will be very helpful when you solve problems. One of them is that the speed of light c is equal to E by B. What is E? E is the electric field and B is the magnetic field. Can any one of you tell me what was the equation which we saw in the previous slide? E is equal to,
So what you said?
can any one of you tell me the equation which we saw in the previous slide? E in terms of its peak value.
E
E
equal to
equal,
E naught
hmm,
sine 2 pi by lambda into
hmm,
Ct minus x.
E minus x. And what was B?
Same V equal to B naught sine 2 pi by lambda into Ct minus x.
Into Ct minus x. So sine 2 pi by lambda into Ct minus x gets cancelled. So this is same as E naught by B naught. So we can get the speed of light as equal to E by B or E naught by B naught. Or another equation that connects speed of light with the electric and magnetic quantities, C is equal to 1 by root of mu naught epsilon naught. Do you remember what is mu naught? What is mu naught? It's the magnetic permeability of free space. And what is epsilon naught? It is the
permeability in medium.
electric permittivity of free space. Naught means it should be vacuum or free space. So C is the speed of light in vacuum. So C is equal to 1 by root of mu naught epsilon naught. Here, to get the value of C in vacuum, you have to substitute the value of magnetic permeability mu naught and electric permittivity epsilon naught. So when you substitute these values, which are constant, you will get this constant value 3 into 10 raised to 8 meter per second. This dots here means multiplication. And if you are considering the speed of light in any other medium, then V is equal to 1 by root of mu epsilon. So if you are taking any other medium, you can find the velocity of light in that medium by substituting the value of the magnetic permeability in that particular medium and the electric permittivity in that particular medium. And there is one common equation. Have you learned this equation before? C is equal to F lambda.
Yes, teacher.
Yes, you have learned this as the common equation for any wave. So if we consider
Yes.
light as a wave, this equation will be applicable for light as well. So C is equal to F lambda, where F is the frequency and lambda is the wavelength. So these three equations of speed of light will help you solve many problems. So will you remember these? These are simple equations, right?
Yes.
Okay.
Yes,
So
teacher.
let us see more about electromagnetic waves. One important quantity which you haven't learned before related to electromagnetic waves is the Poynting vector. So a Poynting vector is defined as S is equal to 1 by mu naught E cross B. So the Poynting vector is denoted by the letter S. As you can see here, it's a vector. And it is obtained as 1 by mu naught E cross B. See, here we are taking the vector product of the vectors, electric field and magnetic field. So what is E cross B? E cross B is EB sine theta, where theta is the angle between them, right? What will be the angle between E and B in the case of an electromagnetic wave?
90.
90. What is sine 90?
1.
1. So we can represent the Poynting vector's magnitude as S is equal to 1 by mu naught E into B. Okay, where E and B are the magnitudes of electric and magnetic fields. And this magnitude varies with time because electric and magnetic fields are varying with time. They are like sine waves, right? And its magnitude reaches a maximum at the same instant as electric and magnetic field. We saw in the previous slide that here you can see the electric and magnetic field goes to its peak value at the same time, and they come back to zero at the same time. Again, they go to the maximum value in the opposite direction at the same time. So electric and magnetic fields reaches the maximum value and goes to zero at the same time. So the angle between them always remains 90 degree. So S is equal to 1 by mu naught EB. And we have already learned that H, which is magnetic intensity, is equal to B by mu naught. When we learned about different terms related to the magnetic field, we learned the magnetic intensity at any place is equal to B by mu naught. So we can write from this equation instead of B by mu naught H. So this is another equation for Poynting vector. S is equal to EH. And the SI unit of Poynting vector is Weber per meter square. Here W is for Weber. Weber per meter square, and it is a vector quantity and its direction is in the direction of propagation of the wave. We know earlier that the velocity of light is in a direction perpendicular to both E and B. That is, the velocity of the light wave and the Poynting vector's direction will be same. So velocity has the direction as that of E cross B. S also has the direction of E cross B. So this is a new quantity which is called Poynting vector. So what is a Poynting vector? If you are asked what's a Poynting vector, who can tell me? You can tell that Poynting vector is a vector that is in the direction of propagation of the wave, and it is defined as S is equal to 1 by mu naught E cross B. Or in other words, vector S is equal to E cross H. B by mu naught can be expressed as H. Okay, is this clear to you?
Yes, teacher.
Okay, so let us see another detailed description of electromagnetic waves. Have you seen electromagnetic spectrum before?
Yes.
Yes.
Yes,
Yeah.
teacher.
You haven't learned that in grade 10?
Yes, teacher, the hydrogen spectrum, right? That one only, right? The which one will be red color, which one will be green color?
That is, you are talking about the spectrum of white light. Haven't you learned the whole electromagnetic spectrum before?
Yeah, teacher, we learned. I mean, we saw. We didn't learn by heart.
You didn't learn in details. This is electromagnetic spectrum. Electromagnetic spectrum means the range of frequencies of electromagnetic radiation. So here, all these are electromagnetic radiations. Which are they? Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio waves, which are short, and FM radio waves, AM radio waves. So together I'm mentioning this as radio waves. So you have to know this order. Here you can see the frequency line. See, it starts from 10 here, the least value, and it increases 10 raised to 2, 10 raised to 4 like that, and goes up to 10 raised to 23. So here, frequency increases as we go up. And see the wavelength. As we go up, what happens to the wavelength? Is it increasing or decreasing?
Decreasing.
It is decreasing. So for gamma rays, it has the maximum frequency. And what about its wavelength?
Minimum.
It is minimum. So any radiation which has high frequency will have less wavelength. But we know the speed of all these electromagnetic radiations are the same. That is, the product of frequency and wavelength will remain a constant. So if you are considering a wave of high frequency, its wavelength will be less. So here, visible light becomes only a very small part of the electromagnetic spectrum. You should know this order in which the spectrum is arranged. Either learn it as radio waves, microwaves, infra, visible, ultraviolet, X-rays, gamma rays, or the other way. Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Let me ask you one question. Which of these waves have the maximum wavelength? Which of the
Long radio waves.
electromagnetic waves have maximum wavelength?
Long radio waves.
Long radio waves. Radio waves, we know that radio waves are used for communication, right? They have to travel long distances. So their wavelength is large. They can travel through long distances without getting scattered. And which of the radiations have least wavelength?
Gamma rays.
Gamma rays. Gamma rays are having very high frequency but least wavelength. High frequency means their energy is very high. They are usually emitted during nuclear radiations. They are emitted as nuclear radiations during radioactivity. They are highly dangerous. So when there are gamma rays, it will travel only for a short distance. Their wavelength is very small. They have high frequency, high energy. They are dangerous. When they get into our skin, they can kill the cells. So they travel only for a short distance. Their wavelength is very small. So you can remember like that, the longest waves are the radio waves and the shortest waves are the gamma waves. Okay, now can you mention one radiation which has frequency more than ultraviolet?
X-ray.
X-rays. So you have to compare these radiations and study them. Now here I have expanded and shown the visible spectrum. You can see here, right? Which of these colors have, which color has maximum wavelength? Look here and tell me. Which color has maximum wavelength?
400 nanometer. No, 700 nanometer.
Yeah, which has?
Red.
Red. So red has the maximum wavelength. Which has minimum wavelength?
Violet.
Violet. Now, can you guess about blue and green? I'm asking about blue and green color. Which will have more frequency, blue or green? Irfan,
Blue.
tell me which will have more frequency, blue or green?
Blue.
Blue will have more frequency because blue has lesser wavelength than green. So you need to know this. This you already know, VIBGYOR, right? VIBGYOR, the colors. And you have to know which has more wavelength, which has less wavelength. And so you learn this in the order of wavelength. Just remember that red has maximum wavelength. So which color will have minimum frequency?
Red.
Red.
Red. So that is why the signals are all red in color. They have maximum wavelength, so they can travel through a large distance and reach our eyes. If you keep blue or violet color as a signal, it will get scattered away easily because their wavelength is small. They cannot travel through a large distance. See, can you name one electromagnetic radiation which has wavelength more than red? Can you name one radiation which has more wavelength than red?
There is no
Ultraviolet.
Ultraviolet have more wavelength than red?
No, no,
Up.
no, infrared. More or less.
Infrared.
Okay.
See, visible light we
Can you
use.
repeat the question?
My question was, can you name a electromagnetic radiation which has more wavelength than red? So, infrared. So for very distant photography, for example, we have to take the photograph of Earth from moon or a different satellite. In that case, we take infrared radiation because they have wavelength even more than red. So they have to travel a larger distance. So microwaves, they are used for satellite communication because they have to go a larger distance. Radio waves also we are using for satellite communication and communication through large distances. So all the waves
Teacher,
which need to travel a long distance have large wavelength and they have short
teacher,
frequency. Yes.
what is AM radio?
Amplitude modulated.
Okay.
AM. FM is frequency modulated. We need not focus on those details. You can consider all these as radio waves. Okay, you will learn later in your one of the chapters. We will learn about modulation and all, amplitude modulation and frequency modulation. We will learn later. Okay. This is just the name given because when they are carrying through a large distance, they couple it with some carrier wave. And how they are coupled with the carrier wave, depending on them, that is called amplitude modulated or frequency modulated. You will learn that later. So this is the electromagnetic spectrum. Now we will learn more about each of these electromagnetic radiations, how they are produced and how they are detected. Can you see the table here? Can you see the table?
Yes.
So radio waves. How are radio waves produced? Radio waves are produced by the rapid acceleration and deceleration of electrons in aerials. What are aerials? Have you seen aerials?
Teacher,
Yes.
it's 41.
Yeah. Okay, I'll stop now. We will learn more about the properties of electromagnetic radiations in the next chapter. Okay. So,